Hello and welcome to this lecture. In this lecture, we're going to study some 2 or 3 very crucial properties in all of linear algebra. The first one is called span, and we have to get a really good understanding of what span is. The next one is the notion of vector subspaces. These are also extremely crucial and fundamental. And finally, most fundamental ideas, linear dependence and linear independence. So, crucial lecture. Let's go through these ideas and build them up slowly as we've been always doing. Okay, what is span, or if you want to be very precise, you can say linear span. Okay, so if you have a set of vectors in R2, okay, in fact, we will generalize later on, but right now we are in the R2 world, right? So in R2, the real plane, let's say you have a set of vectors, you can define a span for them, the span of these vectors. Here is a precise writing down. I've written down vectors v1, v2, v3 as a1, a2, b1, b2, c1, c2, so on, right? Maybe there are more and more of these vectors in the set. Okay, if you have only one vector, okay, just one vector, just take this v1, the span of v1, okay, span of one vector is basically set of all linear combinations of v1. Okay, so if you only have v1, what are all the possible linear combinations you can do? You can only multiply, right? You can multiply v1 with alpha, where alpha is any real number. So the set of all linear combinations of v1, which is defined as the span of v1, is very easy to write down. So set of all alpha v1, so alpha a1, alpha a2 for all alpha in real. Okay, so all scalings, you take this a1, a2 and keep scaling it with different numbers, you get the span. Okay, so basically this notion is the most important notion. So span is the set of all linear combinations of what you have. If you have only v1, the only linear combinations you can do is scaling it with alpha, and that is the span. Okay, set of all linear combinations of v1. You can do v1, v2. What is the span of v1 and v2? The set of all linear combinations of v1 and v2. Now, when you have v1 and v2, you can do alpha v1 plus beta v2, right? You can do this kind of a linear combination. Okay, you can do scaling and you can also do some addition, which is non-trivial. So here you can't, even if you add, it's alpha v1 plus alpha prime v1, you only get alpha plus alpha prime v1, which is again another scaling. Okay, so you don't really get the addition. So here when you have v1 and v2, you can do alpha v1 plus beta v2. Okay, so which is, if you write in the column form, it's alpha a1 plus beta b1, alpha a2 plus beta b2, right? So this is the linear combination. So all of these is alpha and beta have to go through all the real numbers. Okay, so this might end up being a very large set. Okay, so set of all linear combinations of v1 and v2. So span is always defined as a set of all linear combinations of what you feed it. Okay, so you give it v1, it will do all linear combinations of v1. Give it v1 and v2, span is going to be all the linear combinations of v1 and v2. If you do v1, v2, v3, what am I going to say? I'm going to repeat the same thing over and over again, set of all linear combinations of v1 and v2 and v3. So now you have alpha, beta, gamma, right? So alpha v1 plus beta v2 plus gamma v3, just taking linear combinations. Okay, and if you write it in column form, you get alpha a1 plus beta b1 plus gamma c1, alpha a2 plus beta b2 plus gamma c1, alpha, beta, gamma in the reals. Okay, so it's again seems like a very big set. Okay, and you can also many more. So if instead of v1, v2, v3, you have v1, v2, v3, comma dot no, v4, v5, so on, you can simply define the linear span in the same way. Okay, so if any finite number of vectors here, you can very easily handle in this fashion. Okay, I hope definition of span is clear. It's very simple set of all linear combinations of the vectors. It looks like this set may be very huge, but then we will try to understand this set. So understanding these sets is very important notion in linear algebra. Okay, so let's try to understand these sets going one step at a time. Our standard approach in these math courses has been to take the easy cases first and slowly build using logic and intuition and extension. You go to more and more complicated cases. Okay, so let's look at the span of one of the simplest possible vectors that is there, which is the origin. Okay, 0, 0. Okay, so what is the span of the origin? If you just feed the origin, you have to look at all possible scaling, right? This is just one vector. So you have to multiply by all possible real numbers. But if you multiply by all possible real numbers, what are you going to get? You will only get 0, 0, right? Whatever you take 0, 0 and keep multiplying, you're going to get 0, 0. So trivially, the span of the origin is the origin itself. Okay, so we'll also call the origin as the 0 vector, or I'll simply say 0. Okay, so if I say 0 in the context of real numbers, it's the 0 real number. If I say 0 in the context of R2, it means the origin 0, 0. Okay, the all 0 vector. Okay, so this seems like a very easy, nice case. Good, we got our feet wet. Let's try and be a little bit more ambitious. we'll look at AB, a vector AB, where AB is not the origin, somewhere outside. Okay, what's going to be the span of AB? Okay, take an AB which is not the origin, and span of this is all possible scalings of this. We have seen this before, right? When you scale this by all possible real numbers, what do you get? A non-zero point, you multiply by all possible real numbers, you're going to get the line through origin and AB, right? So this is the line that you get. So notice what happens here. Span of the origin is just the origin. Span of any non-zero point in R2 becomes a line. Okay, it becomes a line through the origin and that point. Okay, just the span operation, all possible scales, it gives you that. Okay, I hope it's clear. So these two cases are very, very easy cases. Now let's look at a slightly more complicated looking case, but it will also end up being very simple. Okay, span of the two vectors 1, 0 and 0, 1. Okay, so 1, 0 is this vector. Okay, I have not shown the arrow here, but this is the vector. 0, 1 is this vector, right? This vector. Okay, I have shown just the dot here just to indicate the 1, 0 and 0, 1 point. If you do all possible linear combinations of 1, 0 and 0, 1, what are you going to get? Actually, you get a very simple answer, right? The span is alpha times 0, 1 plus beta times 0, okay, which is actually alpha, and then alpha times 0 plus beta times 1, right? So you multiply the first vector by alpha, the second vector by beta, and add it. So you end up getting just alpha beta. Okay. So the span of 1, 0, 0, 1 is the set of all alpha beta where alpha and beta are R. What is that set of all alpha beta when alpha and beta are R? That is nothing but R2, right? The entire real plane. So the span of 1, 0, 0, 1 is the entire real plane. Okay. So notice what we have achieved here. We have achieved here a lot of efficiency in specifying R2. So previously in R2, you had to give every possible real number alpha beta and say, you know, every alpha beta where alpha is real, beta is real is R2, and we didn't simplify the specification more. So here we are able to say just two vectors. Okay, you take the span of 1, 0 and 0, 1, what do you get? You get the whole R2. Okay, instead of keeping saying, listing out all the possible real points, thinking of it as a big one, it ends up being linearly generated by just 1, 0 and 0, 1. So span is like generation. No, you generate all the vectors in R2 by linear combination of 1, 0, 0, 1. Okay, just to tell you that any point can be generated, I'm showing you very explicitly. If you have a point x, y, how do you generate it as a span as a linear combination of 1, 0, 0, 1? It's very trivial, right? You take x, y, you multiply x with 1, 0 and y with 0, 1, you get x, y. So any point is actually a linear combination of 1, 0 and 0, 1. Okay, so this is at the heart of the power of linear combinations. Okay, even if you have an infinite number of points like you do in R2, you can address every point with just two vectors. Okay, 1, 0 and 0, 1. Any point can be a linear combination of 1, 0 and 0, 1. Okay, this little idea in R2 seems very trivial, but you will see it will expand into a bigger one as we go to larger vector space. Okay, so a large set can be very efficiently specified as the span of two vectors or few vectors. Okay, so 1, 0, 0, 1. Right, so keep this in mind. So we have found three easy spans. Origin is very simple and boring. AB is a little bit interesting. You get a line through the origin. But once you go to 1, 0, 0, 1, you seem to be getting the entire real plane R2. Okay, so now you may wonder what other possible spans can there be. You have other vectors coming in. If you define other spans, what else you can get? It turns out, very interestingly, these are the only three spans. Whatever may be your vectors, okay, it might be a little bit non-trivial at this point. You'll see it's easy enough to show. Whatever may be the vector in R2, if you take a span of any set of vectors, you will either get the origin, or you'll get the line through the origin, or you'll get the entire R2. You can't get anything else. Okay, so spans looks like it's simplifying your understanding of the vector space in a tremendous fashion, isn't it? So let's see more of how to show this. Okay, so let's look at span of more complicated vectors, looking vectors than this. Okay, so to do that, we need a couple of important properties of span. So you remember, anytime we wanted to extend our results, we have to think logically about extending some ideas and understanding of what the defined object is. Okay, so here is the crucial observation. The first property is, if you have a span of a set of vectors v1, v2, v3 like that, if you multiply the first vector, let's say v1, okay, it can be any other vector also, I'm just showing you with the first one. If you multiply a vector with a non-zero number a, you will get the same span. The span will not change. Whether you have v1, v2, v3 or a v1, v2, v3, the span will be the same. In fact, you can multiply by non-zero vectors for every vector and the span will not change, right. So, why is that? Because if you take a linear combination of v1, v2, v3 etc., okay, it is the same if as long as this A is non-zero, it is the same as a linear combination of a v1, v2, v3 etc., right, because I can change this constant that is multiplying a v1 to alpha by a. Okay, I had alpha v1, I multiplied this v1 by a, but I know division is possible in my scalar field, so I take this a, I divide by a, so I get alpha by a. Okay, so you see, notice how based on this very trivial looking observation, span of set of vectors, if you multiply any vector by constant or maybe even more than one vector by constant, non-zero scalar, you get the same span. Okay, seems like a trivial result. You'll see how we'll apply these results very smartly to get get a better understanding of span. Here is the next property which is even more crucial. Okay, if you have v1, v2, v3, and here what I'm doing, I'm keeping v2, v3 and all exactly the same. Instead of v1, I'm making it v1 plus a v2, okay, and this a can be anything now, 0, non-zero, okay. So, v1 plus a v2. So, I'm doing only a linear combination of v1 and v2, but I've kept v1 with no other coefficient multiplying, v2 alone is a v2. These two spans are the same, okay. Again, the proof is very easy. You can just observe that this linear combination is also a linear combination of v1 plus a v2, v2, v3 etc. Okay, you just have to do this addition and subtraction and then you will quickly see this, right. So, instead of v1 plus a v2, I put alpha and then I have this alpha a v2 additional, I subtracted, I get the same thing, right. So, this and this are exactly the same. You see that this thing cancels and you get the same thing. So, on the face of it, you may not think that these properties are so crucial, but you see that the way I scale, I'm allowed to scale vectors, span does not change. I'm allowed to combine vectors, span does not change, and that has a very huge impact on our understanding of a span, particularly the second step. Okay, so this property 1 is loosely called scaling, property 2 is loosely called an elimination type step. So, you'll see why elimination is so enough. Okay, so we're going to exploit these two properties and improve our understanding of span. So far we've had span of 1, 0, 0, 1. How do you go beyond that? We're going to use these properties. Okay, so here is our first attempt. Okay, we're going towards the general case. So, here is, instead of saying 1, 0, 0, 1, I'm going to take 1a as v1 and 0, 1 as v2. Okay, notice what I've done here. Instead of, if this a were 0, it's easy, right? You're going to get R2. If this a is anything else other than 0, what will happen? Okay, so if you want to picture these two vectors, v1 is 0, v2 is 0, 1, so it's the same as before, but v1 instead of this canonical thing, it can become any 1a, right. So, it is gone, it's x equals 1, but then x coordinate is 1, y coordinate can be any a, it can be up here, it can be down here, it can go anywhere. I'm just showing you one possibility. Okay, so v2 here, v1 here. Okay, so what is the span of v1, v2 when v2 is like this, v1 is like this? Okay, it looks a little complicated, but it turns out you can reduce it to the previous case. This is the same as span of 1, 0, 0, 1. How? I'm going to use my property 2. Okay, I had this wonderful property 2 that I can do elimination, I can do a combination of v1, v2 and the span does not change, but I'm going to do it very cleverly. So, notice what I've done here. Instead of doing v1 plus a v2, I'm doing v1 minus a v2. This is allowed, right? For any a I can do this thing. So, I can do v1 minus a v2. Okay, instead of that v1 plus a2, instead of thinking a as positive, you think of a as negative, right? So, it becomes minus. Okay, so I do v1 minus a v2. Okay, so when I do v1 minus a v2, you notice that this very interesting thing happens. This 1 remains the same, 1 minus 0, but the second a minus a times 1, it goes off to 0. Okay, so that's why this v1 minus a v2 like combination, when this a is here, is called an elimination step. You eliminate a non-zero value and make it 0. Okay, so once you do that, by our property 2, I know the span of 1a 0 1 is the same as span of 1 0 0. And what is span of 1 0 0 1? It's the entire R2. Okay, so notice how we are using these clever observations and logic to build up on our span. We had 1 0 0 1 very easy, but 1a 0 1 is also R2. Okay, so you can prove it in various ways, but I'm just showing you the general method of elimination, and we haven't yet used scaling. I'm going to use scaling shortly. Okay, so let's look at one more case. Here is a simple extension of this 1a 0 1. So notice what I'm doing here. I'm going to look at this kind of a case. Delta 0 is the first vector and b1 is the other vector. Okay, so this is actually very, very similar to this. I mean, don't be misled by where I am putting the 0. Okay, it doesn't matter where I put the 0, right? I can suitably eliminate to convert this to that, right? B1 and delta 0. But what you can quickly argue is by property 1, I can scale the first point as long as delta is not 0. I can scale the first vector by 1 by delta, right? If I multiply this by 1 by delta, I am going to get 1 0 again. So I have 1 0 B1 and that's the same as 1A 0 1, right? 1 0 B1 is the same as 1A 0 1. Think about it. If this is V1, this is V2, this is 1 0 B1, I can do V2 minus BV1, right? If I do V2 minus BV1, my B will get eliminated. So, I will go to 1 0 0 1 and this becomes R2. I hope you can see this elimination process. This and this are exactly the same. Think this through. It's a little bit of an exercise. Think about why this works. This is working. So, 1 0 0 1, 1A 0 1, delta 0 B1, all of these guys have R2 as the span. Okay, so notice how we are expanding our set of vectors. Okay, so let's see one more, which is slightly more tricky. So I'm going to do 1A B1. Okay, so far I had 1A 0 1 that seemed easy, but I have 1A B1. So this A and B are entering the picture. Okay, so if you want to plot, it's going to be 1A here and B1 B1 here. Okay, V1 and V2. But it depends, you know, I don't know where A and B are, I don't know what can happen here, you know, some interesting crazy things may happen, right? For instance, you're already seeing some interesting things, right? Depends on the value of A, B. So A and B are both 1, then these two vectors are going to coincide, maybe the span will be something else. If A and B are not 1, then interesting things happen. A and B could be 0, in which case you get the canonical basis, you get, so many possibilities are there. How do you characterize the span of 1A, B1? Okay. So here again we will use our elimination process very, very carefully. So notice what I am doing here, I am making this A as 0. So V1 minus AV2. So I have, when I do this, the bottom coordinate becomes 0, this A becomes 0 like before. But then this 1, which was 1 here, is not the 1, right? Because this B is entering the picture. So when you do A times V2, I get 1 minus AB instead of the 1. Is that okay? I am multiplying V2 by A and then doing a subtraction. So I get this going away. This will be 1 minus AB. So notice this guy, now this one looks very much like this, right? So this 1 minus AB now controls how the span is going to behave, right? If this 1 minus AB is 0, then I have only this B1 and the 0 will play no role, right? The 0 is like origin is useless, you can throw it out, so span of B1. But if this 1 minus AB is not 0, then you get this kind of a picture and you get R2. Okay, so that's what happens to these guys. So if you want to ask what this is, it depends on 1 minus AB. So if 1 minus AB is 0, then the answer is that the span 1A1 1A B1 is actually span of B1. Okay. In case 1 minus AB is not 0, you get the entire R2. Okay. So basically what's going on here is when 1 minus AB is equal to 0, B is 1 by A, isn't it? Right? B is equal to 1 by A. So if B is 1 by A, right, if B is 1 by A and then you multiply this vector by A, you will get 1A, isn't it? If AB is 1 and you multiply this vector B1 by A, ABA you get, but AB is 1, so you get 1A. So these two are actually on the same line through the origin. They lie along the same direction. Okay. So when two vectors lie along the same direction, their span is going to be the span of just one vector and you get just span of B1. But when 1 minus AB is not equal to 0, these two end up lying in different directions and you get the entire R2. Okay, so this notion is sort of crucially important. So as you move towards the general case, you're going to get some number like this, like 1 minus AB. Something has to be non-zero or 0, okay, which determines whether the two vectors are on the same line or not, okay. And that is going to decide whether or not the span is going to be the line or the entire R2. Okay, so you can see where I'm going. So it seems to be building up very slowly. Now I think we're ready to finalize the process of elimination in the general case. We're going to move towards the general case. We're going to look at A1, A2, B1, B2. A1, A2 is the vector V1, B1, B2 is the vector V2. Okay, how do we do elimination in the general case? Okay, so it seems a little confusing. So first step we'll do is to consider easy cases. Okay, so if A1 and A2 are both 0, the easy case, then you just get span of V2, which is the line through the origin. Okay, so things become interesting only when one of these two is non-zero. So the next case to consider is if A2 is non-zero. If A2 is non-zero, I can divide by A2, right? So that is the crucial idea here. So if A2 is non-zero, I'll divide by A2, okay? I'll end up getting A1 by A2 1, B1 B2. So now we are going towards our known cases. When I have something like this, I can eliminate this B2, isn't it? So notice this, whenever you have one B2, you should immediately think of elimination. I can do V2 minus B2 times V1 by A2, and then my B2 will get eliminated. So that's my next step. Okay, so I use property 1 here to divide by A2, because A2 is non-zero, then property 2 here to eliminate this B2 and make it 0. But remember, when I multiply by B2, I get B1 minus B2 A1 by A2 here. Okay, so now this guy, as you know, is going to control the span, this fellow, right? So if that guy is non-zero, this B1, if that guy is 0, then you just get the span of V1. Okay, span of A1 by A2 1, which is span of same as span of V1, right? It's just division by A2, right? V1 by A2. Okay. So the other case is when this is non-zero. If this is non-zero, then you get the entire R2. Okay. So I hope you saw this process of elimination. It's a simple sequence of arguments using the same ideas as before, but you get this condition. And notice this condition has become a little bit more general than what we had before, right? We had 1 minus AB before. So now you have B1 minus B2 A1 by A2 equal to 0. Okay. So you can simplify this. You can write it as A2 B1 minus B2 A1 equal to 0, right? Multiply both sides by A2. A2 is not 0. So multiply both sides by A2. You get A2 B1 minus B2 A1 equal to 0. Okay. Here also you get A2 B1 minus B2 A1 not equal to 0, or A2 B1 not equal to B2 A1. Okay. These are various ways of rewriting this inequality. What about A1 not equal to 0? It's the same case, I mean, A1 is not equal to 0. Instead of dividing by A2, you're going to divide by A1 here, and everything else remains the same. It's the same thing. I'm not repeating this big step. You just do divide by A1, and then you eliminate B1 here, and then you get the same condition. Okay, again, everything will depend on whether B2 minus B1 A2 by A1 is 0, which is the same as A1 B2 minus B1 A2, right? Same thing as before. Okay, so if this quantity, these two are the same. Okay, this equation and this equation are the exact same things. So I hope you see that this case 1a and case 2a are the same condition, right? You get the A1 B2 minus B1 A2. So this A1 not being 0, A2 not being 0 are exactly the same thing. Just replace some small things. You get span of V1 in this case, and then if this were not 0, then you get R2. So both these cases are actually exactly the same, just they came about slightly differently. Okay, so let's summarize this. If you have two vectors A1, A2, B1, B2, B1 and B2 are these two vectors, how does their span behave? Everything depends on A1, B2 minus A2, B1. So that controls everything. A1, B2 minus A2, B1, right? This diagonal sort of thing. If this is 0, then you have interesting cases. How can this be 0? How can A1, B2 minus A2, B1 be 0? Both these vectors can be 0. Then the span becomes the origin. Okay, so it's an easy case. Or you may have one vector being 0, the other being non-zero. Right? V1 is 0, V2 is non-zero, or V1 is non-zero, V2 is 0. Then in that case, this if V1 is 0 and V2 is non-zero, you will get span of V2. If V1 is non-zero, V2 is 0, you will get span of V1. Okay. Or you may have V1 and V2 in the same direction. In all these three cases, when A1, B2 minus A2, B1 is 0, you will get span as a line through the origin. If both are 0, then it's a boring case, span is origin. If one of these is non-zero, either this can happen, or you may have V1 and V2 having the same direction, in which case span is a line through the origin. Okay. And the final case is when A1, B2 minus A2, B1 is not equal to 0. If it is not equal to 0, V1 and V2 are in different directions, and span is the entire plane. Okay. So one of these things being 0, right? These three cases are a bit boring. You can just rule it out. You can say if one of these is 0, what is the point, right? You immediately know the answer. There's no need to do anything. Okay, so these two are very interesting. If V1 and V2 are both non-zero, then it depends on whether or not they are in the same direction. And that is easily verified by this condition, A1, B2 not equal to A1, A2, B1, they are not in the same direction, right? Another way to read A1, B2 and A2, B1 is, if all these are non-zero, A1, A2, B1, B2, then you can divide by A2. So you say A1 by A2 equals B1 by B2, right? A1 by A2 equals B1 by B2. That's the same as this condition. I hope you see that. Okay. So if V1 and V2 are in the same direction, A1 by A2 equals B1 by B2, then the span is a line through the origin, right? That they are in the same line, so you get that. If it is not 0, A1 B2 minus A2 B1 is not equal to 0, V1 and V2 are in different directions, and you end up having the span being the entire plane R2. So notice how the span is working out to only one of these three possibilities, like I mentioned before. Okay, so hopefully this showed you how you can use simple logic to build up on the span. Okay, so we're going to do a little bit. So this concludes our discussion of the span. In the next lecture, we're going to see illustration of how to do this elimination in actual cases.